Hello everyone, my name is Fernando Pereira, and this is the last part of our series on research on tensor compilers at UFMG. Today, I will tell you about the sparsity propagation analysis that we have designed and implemented at UFMG. We designed this analysis for the tensor algebra compiler, the TACO compiler, as it's called. TACO is a code generator that takes high-level tensor expressions like these in the figure as input. This notation is called the tensor index notation. It then produces optimized C code to implement the computation, so it translates high-level tensor expressions into optimized C loops. TACO was created by Frederick Kjostad. He was an MIT PhD student under the supervision of Saman Namara Singh. TACO is specifically designed to be very good at sparse computations. It was built from the ground up to efficiently handle operations where most of the data values are zeros. This is its primary strength and the main reason it was created, and also the reason why you choose it to work with it. So, what's sparsity? We say that a tensor is sparse when most of its elements are zeros. Here's an example of a 3D tensor with lots of zeros. There are many ways to represent these sparse tensors. For instance, we can organize them in trees with one level per mode. Mode in this case are each of the dimensions of the tensor. Here's an example of a data structure called a compressed sparse fiber, which indexes the data in the tensor a bit like a trie does. Imagine that each index of a non-zero element is a string. Then we can represent these elements using a prefix tree on these strings. And there are many ways of organizing these trees. Depending on our choice of which level corresponds to which mode, we might have more or less efficient storages. So an important question is how to decide on the right tensor representation. For that, it helps to know how zeros propagate throughout the computational graph. We can run the program, of course, to know that, but usually this is very expensive. So is there a static approach to infer zeros in computational graphs, provided that we know some of its inputs? That's the goal of this project. We designed a static analysis to estimate zeros in computational graphs. In this case, we infer which tensor slices contain only zeros. Let me explain what a tensor slice is with an example. Let's consider this 3x8 matrix in the figure here. A tensor slice in this case is like a subtensor where we fix all the indices but one. In this case, we have two indices. Then each slice will be a vector. We have one slice per each column of the matrix and one slice per each row. Now we can try to estimate which slices contain only zeros. Let's associate this information with each slice. If we associate it with a zero, then that means that the slice only contains zeros. Otherwise, if we associate it with 1, then the slice might contain non-zero elements. Now, given a computational graph, we want to infer which slices are sparse. We can assume that we know the operands. These are the operands of the computational graph, like matrix mole, addition, ReLU, and such. We can also assume that we know the inputs of the computational graph, for instance, either via profiling or via user annotations. However, we don't know anything about the tensors that are produced as results of computations. Given the scenario, what is it that we can learn about the computational graph? We can reason about the inputs and the semantics of the operators to infer how zeros propagate throughout the computational graph. For instance, in this example, the second line in the input forces the second line of the output to be formed by zeros. This is what we call forward inference, because the knowledge of the inputs of an operation let us infer something about the output of that operation. Now let's look into this line on the second operand of the multiplication. If we know that it only contains zeros, what else can we infer? Well, essentially, the elements of the last column of the first operand can be anything. These values don't matter for the computation because they will be multiplying zeros anyway. Thus, we can simply treat them as zero as well. This is what we call lateral propagation. In this case, the knowledge about an operand let us infer something about the other operand of that operation. Finally, if for any reason we know that this line of the product is all zeros, what can we learn? Well, in this case, we learn that the second line of the input can be all zeros too. The fact that somehow we had already concluded that the product had a line of zeros, so regardless of what we have as inputs, the second line of the input is contributing to form a line of zeros only. Thus, we can treat that as don't care elements. I mean, we can treat these elements in blue as zeros or as anything. That does not matter, for they are only being used to produce zeros anyway. This is what we call backward propagation, where the knowledge of the result contributes to infer information about the operand. So in the end, we have a system that propagates information in multiple dimensions, along multiple directions, I mean to say. We have the classic forward propagation, where knowledge about operands let us infer something about the results. We have lateral propagation, where we transmit information across operands of the same operation. And we have backward propagation, where knowledge about the result let us infer something about the operands. Notice that forward propagation infers elements that are really zeros, but lateral and backward propagation infer elements that are don't cares. We can treat them as zeros or as anything because they don't really have observable effects. We don't need them, we don't need to store them. We have these lateral and backward propagations in operations that we can group into semirings. A semiring is an algebraic object formed by a set and two operations. One of these operations is similar to addition and the other is similar to multiplication. There are many semirings. In our case, the one that's most important is formed by addition and multiplication, but there are others. Something important to say is that we can infer sparsity very fast. That's asymptotically faster than running the computational graph. Let me show you some results. Here I'm taking benchmarks from the ISUM collection, which contains lots of operations that contract and multiply tensors. Even though some of these benchmarks are very large, sparsity propagation analysis takes milliseconds. I mean orders of magnitude less than the time that it takes to compile these computational graphs using Tackle, for instance. And still orders of magnitude less time than it takes to run the computational graphs themselves. This is the story of profiling versus inference, because we could obtain sparse information by running the computational graph on Boolean tensors, for instance. But static analysis is asymptotically faster than profiling, even if we consider a Boolean representation of each tensor where we store and evaluate operations very efficiently. And you might ask, okay, but what can you obtain any speed up by using sparsity propagation analysis to enable optimizations? And I say, yes, you can. Here I'm showing some results that we got after running these benchmarks. I have three versions of each benchmark: a dense version, which is the normal representation of the computational graph. Then we have two implementations based on compressed sparse fibers. What we call sparse is a representation where we only know sparsity information about the inputs. And what I call sparse plus propagation is a version where we use the static analysis to infer sparsity on intermediate tensors. If the level of sparsity is small, then of course it's better to simply use the dense representation. However, if we can prove that a slice is sparse, then we can remove it from the fiber tree. This avoids computations and reduces memory storage. Once we increase the level of sparsity, this trade-off becomes clearer. At around 50% of sparsity on the inputs, our propagation let us remove more fibers and we start to observe speedups. This analysis is implemented in Tackle, as I had mentioned before. You can get it in our repository. And since this month it's also available in MLIR, in the Linog dialect of MLIR, we have sparsity propagation for all the named operations in Linog, thanks to the work of Peter Avagirinus from ICL. All these ideas are available in this paper, which we have published this year in the International Symposium on Code Generation and Optimization. And that closes our series of videos about research on tensor compilers at UFMG. I've discussed contributions to different tensor compilers, including, besides Taco, TVM, XNC, and now MLIR. That's part of our research mission and at UFMG's compilers laboratory, and that's the design and well, this mission is to design and develop techniques that will lead to better tensor compilers. And now, if you have questions, please feel free to send me an email.